Welcome back, physics fans. This is our first lesson in physics. Yes, this is chapter one, lesson one, chapter one, lesson one. Okay, and whenever we start a new topic, almost in anywhere, we need to learn the terminology. So we're going to be using words like kinematics. So in our first paragraph, we'll define that right away. Okay, so let's just basically begin. Here we go. The big topic of physics that we're studying in Physics 11 is called mechanics. Now, mechanics is the study of motion and the objects, and mechanics can be broken down into two parts. The two parts are kinematics and dynamics. These are two different terms. Dynamics studies forces, momentum, and energy, which causes the motion. So dynamics studies causes. Okay, that's the big word there. What causes the motion is dynamics. Kinematics studies the motion itself without being concerned with causes it. So kinematics is the basic study of motion. And that's what we're going to be doing, studying the motion. And it doesn't really, we don't care what causes it without reference to being, so kinematics is without the reference to forces, mass, energy. Okay, and kinematics has the prefix, or actually the root of the word kinema, which comes from the Greek word, and we use that in like cinema, which is motion pictures. Motion pictures, kind of funny, right? Kinematic, study of motion. There we go. So let's just talk some physics talk right now, okay? Two terms we need to learn, opposite in nature, here they are. One is scalar, and the other one is vector. Scalar is the measurement, is a quantity that has a measurement that only has magnitude. Magnitude is like kind of the word size, so it only has size. So magnitude is, so scalar only has size. So let's just give you some examples. So the mass is like 5 kilograms, and the distance is 3 meters. And an example of speed could be 30 kilometers per hour. Okay, my bad. Okay, let's just, so again, 5 different quantities of examples of scalar, things that only have size is like mass, which is like 5 kilograms. Distance, an example is 3 meters. Speed, which is 30 kilometers an hour. Okay, and let's move to energy. Maybe energy could be 500 joules, and I'll spell that out for you instead of just the abbreviation of J. Okay, and that's an example of it. And an example of time could be 10 seconds. So those are all examples of a scalar quantity. A vector quantity, next one, is a measurement that has magnitude, that's again size, but also has direction. Okay, and that's kind of like an arrow, right? It has a direction. So an example of vectors are like position, displacement, velocity, acceleration, and force. So let's just give example properties of each of these. A position would be 5 meters to the right. A displacement could be 3 kilometers east. A velocity could be 30 kilometers per hour north. An acceleration could be 9.8 meters per second squared. Give me a direction for acceleration. We will actually go with down here. I understand you said south and stuff like that. I was just seeing if anyone remembered the 9.8 and the reference that I'm talking to about gravity downwards. And force could be 5 newtons forward. You don't have to know the unit newtons yet. So those are just examples. So vector and scalar. Have you heard of vector before? Vector serial. It's an energy serial, but funny thing that vector serial is an energy serial, but energy is actually a scalar, not a vector. How about this guy? Do you remember him? Yeah? What's his name? What's his name? Vector, yes. So here's so vector committing crimes with magnitude and direction. Okay. So let's just talk about the first quantity that we're measuring is a distance, perhaps. And distance has usually an abbreviation of a letter D, okay, in formulas, and is a measure of the separation between 2 points. And it does not include direction, only the magnitude of the distance. Distance is a scalar quantity because it only has the magnitude. And distance d can also be the measure of how far an object has moved during the total period of time t. So let's just an example here. You kind of recognize this. Well, maybe not. You've never been this high above beforehand. But if I told you that around Dover Bay here, we're going to start in the loop and we're going to walk over to my windows. We're going to stay outside of the building and walk around to the windows. Where would we go? Where are the windows of my classroom? Just kind of think about it. Look at Dover Bay. Where is our classroom? Where are we sitting right now? Those are the windows in the back there. Where is that? Okay. My windows, my windows are right there. Okay. And therefore you guys are kind of seated right here. And since this is going up to the internet, someone could find you. Just kidding. Here we go. So we're here, and we want to walk around to these windows. There's our scale, 20 meters. So if I walked there 20 meters, walk there roughly 20 meters, walk there roughly 20 meters, there, there, there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 of these rough 20-meter chunks. And so that's about 220 meters. That's how far you would have to walk in there to get to our classroom. That's 220 meters. And that would be the distance that you had walked. Okay? That would be the distance that you walked. Was there a direction? Well, yeah, there was lots of different directions, and we're not asking for that. I was asking for the distance, not anything else, which didn't require it. But this was east here, then southeast, and south, southwest, southwest. We curved around the auto shop here and went northwest, northwest. So it was lots of different directions we went. But we're not asked for that. We're asked, what is the distance? How far did you travel in that amount of time? Okay. Now, time, I've thrown a fun definition here that you don't have to memorize. In fact, if you kind of crossed it out, I wouldn't be too far. But that's what we need to know. Time is a scalar quantity. Okay, but let me read out this definition as you hear. Time, also written as a letter T, is a dimension in which events can be ordered from the past through the present into the future. Way above your head, here we go. And also the measure of durations of events and the intervals between them. Time is one of the 7 fundamental physical quantities of the International System of Units and is used to help measure the change of an object. an operational definition of time wherein one as says that observing a certain number of repetitions of one or another standard cyclical event, such as the passage of a free swinging pendulum, like a grandfather's clock swinging back and forth, constitutes one standard unit of something called a second, could be, and is highly useful in the conduct of both advanced experiments and everyday affairs in life. So what do you need from this? Just exactly what I've highlighted here. Time is a scalar quantity, and it's kind of measuring intervals between events. Okay, leave that alone. We have a chapter 1, lesson 4, all about time and calculating time. We'll leave that alone for now. Position, sometimes given a bold P or a P with an arrow over it. That's what we will do because that's a vector, okay? But once I talk about it here, we probably won't use it very much in this course, but we need this to understand how to get to displacement. This is the important one that we're going to be talking a lot about, distance and displacement. Position, though, is a vector quantity, okay? It is a measurement of the distance of an object from a reference point. So it's from a reference point. That's what makes it important. So we have our origin, like in the Cartesian coordinates, our x and y locations, and we say our starting point is at the origin. Okay? The origin. Okay, you don't need to write that down, it's fine, but okay? And then we need to also label the direction that we're going. Okay? And we'll see some examples of that coming up right away. Okay? The direction can be indicated with words or algebraic signs. So even a number line where you have the origin of 0, and then you go 1 and 2 and 3 and -1 and -2. This is also a position on this number line. So if I gave you a -1, the negative would be towards the left. Okay, the -6 could be given as towards the left. Next thing, change in, very tough to understand, okay? But we have that as a symbol in math and physics as this capital Greek letter delta. That's the alpha, beta, gamma, delta, the fourth letter of the Greek alphabet. And it's just a capital triangle, a big triangle. And so delta t, triangle t, delta t would be the change in time. How much time has changed? We just write that as delta t. And to calculate the change in something, we have to take the final measurement and subtract the initial measurement. This is a tough thing to understand sometimes. Our brain does it so fast, but we don't know exactly how we did it. Okay, and I know your brain works it. So like, for instance, if your bank account went from $5 to $1 in one day, the change would be not be $4 because we take the final minus the initial, $1 minus $5, it'd be -4. Our change would be -$4. Okay, so it's how you can do that. You can understand. Oh yeah, it went down $4. That's why it's -4. And how do you actually calculate that -4? We take the final 1 and subtract the initial. So that's what I highlighted. That's the important part. Okay, then let's talk about displacement now. Displacement is a vector. Okay, and displacement is the change in position, and it's calculated by taking the final position of an object and subtracting the initial position of the object. So displacement is final minus initial. Okay, I don't, and if I'm rushing through it, it's on purpose because we don't need to worry so much about that. We'll see when we start doing position and when we start doing speed and velocity, that's where we'll understand the delta signal. But let's just find our displacement here. Final minus the initial. Where did we start? Okay, let's just check out what highlighter can I use here. Can you see this? That's where we started, and this is where we ended. So if I had to draw an arrow that represented the displacement, that would be the arrow. Maybe I can just highlight it this way. Almost. 1 second. Let's see, we'll give it another try. There we go. Pen properties. Let's make it bigger. Boom. That represents the displacement. Okay? Because this is where we started and this is where we ended. And that would be the displacement. Final position minus the initial. Let's talk about speed now. This is where I start slowing down because at this point, this is the meat and potatoes of this lesson, besides the terminology. We get to our first formula. Speed is the rate of change of distance with time, and it is a scalar quantity, no direction. So speed, given the letter v, is how much distance changes with respect to time. If you make sense of it and think about it for a second, we have velocities of like kilometers per hour or meters per second, and we have the distance on the top and the time down below. And the distance up top is how much we've changed in distance. Okay, so but how far you've traveled in that distance and how much time has elapsed. Okay, so we have a formula, and we can get lazy and write v is equal to delta d over the time. Sometimes we even get extremely lazy and write down v equals d over t. We know what this formula represents, and we know that represents a changing distance and a changing time. But the official formula is that. The official one is that. If you start on your worksheets and start writing this formula down, I would be approving of that. It's fine. It's good. That's how I do it sometimes. Velocity is the rate of change of displacement with respect to time. And displacement is a vector quantity. I'll just draw a little arrow over that just to represent that it's a vector. So it turns out that if we put into the same formula the d to be a vector, we get a vector out. If you put a scalar in, you get a scalar out. If you put a vector in, you get a vector out. Okay? And it's really the change of positions. But we don't have to worry about the definition. It is the same formula. So I will go v is equal to d over t in my lazy way of doing it. But we'll know that if this is velocity, this is displacement. Because if we put in a vector of displacement in here, we get a vector out. If you're not following this, you will follow it as we go through it. It becomes very easy. Okay, so that is the one formula that we have right now. I've overdone it here with vector symbols and deltas and stuff like that. It's very convoluted, meaning it's a little difficult to look at. There's so many little pieces of information in there. And when we rearrange the formula, solve it for d, we get velocity times time. So that's another version of the exact same formula. What would time equal if we had to rearrange this formula and solve for time? Okay, it would be d over v. Okay, and that's right. What is one of the characteristics that you always remember here, just to verify that you've rearranged it correctly? D is never in the denominator. D will never be in the denominator. Okay, we have t in the denominator and v, but we never have d. Okay, let's do our last little bit of reading here, and we'll try a couple examples, and then we'll call it timeout while you try some extra things. Speed is similar to velocity, however, it is a scalar quantity, and is the change in distance divided by the elapsed time. Okay, speed and velocities may be equal in magnitude. Okay, so this is a read that you might not get this time that you read through it, but before the test on this chapter in like a week and a half, 2 weeks away from now, we're just starting it today. You will read this. So I would put the words in the column here, read again. Because right now you're just learning this terminology. So when I say speed and velocity, you might not remember what the differences are, even though we just talked about them. But in a week's time, you will get it. So read this again later on so that it might sink in. Speed is similar to velocity, however, it is a scalar quantity and is the change in distance divided by the elapsed time. Speed and velocity can be equal in magnitude. The scalar quantity meaning the same size. So what is it talking about? We could have that the speed is 90 kilometers per hour and the velocity is 90 kilometers per hour north. So this is our speed, this is our velocity. They have the same magnitude, the 90 and the 90, but this is a velocity, so it also needs a direction. So that's what it says. Speed and velocity may be equal in magnitude. The scalar quantity can have a negative value, and the change in this scalar quantity can also be negative. Can we have velocity that is negative? Could we have 90 kilometers an hour north? Negative 90 kilometers an hour north? Well, you could. We'd understand what it is, but it'd be better to write it as 90 kilometers an hour south. So really, we don't get negative velocities. You can, we understand it, it's just not the best. So a speedometer measures speed. How fast that little thing in the car, it measures speed. It's definitely not telling us a direction. But really, a speedometer is not really speed because we need to be able to show negative. If you drive backwards, it doesn't go negative on your car. Anyways, we've gone way high ahead that we don't need to go. Some people might be worrying, but we're going to show you how to do example number 2 here, which is the typical Physics 11 first type of question that you get. What time does it take to travel a football field, which is 100 meters, at school zone speeds? What's a school zone speed? Okay, in Canada here, a school zone speed is 30 kilometers per hour. Okay, 30 kilometers per hour. And we're going to travel 100 meters. How long do you think it'll take? A day? An hour? A minute? A few seconds? You're in a school zone and you're going 100 meters. Just guess right now, don't without a calculator in your head. I would say maybe 5 seconds. 6 seconds. You're just driving right in front of McGurr Elementary, and you're going at the suggested speed. And how far? How long would it take to go 100 meters? How much is 100 meters? Maybe 20 car lengths. Maybe not even that. Yeah, maybe. Who knows? So, what are the steps? You write out the formula. You put the numbers in the formula. You show me the calculations, and you write down the answers with the units. Okay, this is the steps. So what's the formula? Well, there's only one right now. V equals d over t. Okay, let's put the numbers in the formula. D is 100 and speed is 30. Oh, weird units. Let's convert the 30 kilometers per hour to meters per second. The quick way of doing that is you divide it by 3.6. Okay, but let's just show you the right way to do it today, and then we'll show you the shortcut tomorrow. Okay, we multiply this by 1 meter over 1,000 kilometers, and then we multiply this by 1 hour over 3,600 seconds. So this 30 kilometers per hour, 30, you divide it by 1,000 and multiply it by 3,600. And whoops, did I do it wrong? Oh, it's 1 meter is not 1,000 kilometers? No, it's 1,000 meters is 1 kilometer. Oh, okay, so I'm not going close to the speed of sound or 1/3 of the speed of sound going through a school zone? I hope not. 30 times by 1,000 divided by 360, 3,600, sorry. 8.333. How about I just write down 4 sig figs for now? 8.333 meters per second. I won't do too well on today's quiz with that math. So that's our speed, that's our v, and this is our d. So let's plug in the numbers. So I'll put the line here just to separate it. Putting the numbers in, I get v is 8.333 meters per second is equal to, the d is 100 meters, and we want to find the time. And last but not least, let's just rearrange this. We will get t is equal to the 100 meters divided by the 8.333 meters per second. We just cross multiply to bring that up. And then we take the 100 and divide it by this number. The meters will cancel, and we get 1 over 1 over seconds, which makes it equal to seconds. So our time is going to be into seconds. And let's pull up our calculator, and we take 100 divided by that number above, and I get 12. Okay, this is a hard question to begin with because we have to do conversion to begin as well. So that makes it a little bit harder. Okay, when we start doing the worksheet later on tomorrow, there's going to be a lot of easier ones where we don't even have to do the conversion. Okay, now let's do number 3, and then we'll take a break. What velocity must you maintain in meters per second to travel 350 kilometers south in 4.5 hours? Okay, I will first do it this way. Velocity is equal to distance over time. And I'll just separate that. And we get the velocity is distance 350 kilometers south over 4.5 hours. Pull up Mr. Calculator. 350 divided by 4.5, and we get, why do I do times? 350 divided by 4.5 is 77.78. So the answer is 77.78 kilometers per hour. That is the right answer. It's not in the right units, though. They want it in meters per second. So through a conversion, which I'll show you again tomorrow, as I promised. I'm just going to divide this by 3.6 without showing the steps right now. And we get 21.6 meters per second. So the actual answer I was looking for is 21.6 meters per second. And we need that direction south. And that will be our velocity. Okay, thank you very much. Try the examples 4 and 5. We'll talk about them probably tomorrow. Okay, thank you.